graph databases struggle with scale. Load a billion node graph, run a complex query, and watch performance tank. And most systems crumble under large datasets or really complex multi-hop traversals. Kuzu is an embedded graph database which changes this. And it brings modern database techniques to graphs. And it can handle a lot of data with speed. So you can build fast analytics, embedded applications in Android apps, in serverless functions, or also with WASM in the web. You can do quick experiments. So build temporary graphs in memory, process the data on the fly, run analyses without persistence. And it works by taking a lot what we've learned over the years in databases and applying it to graph databases. So similar to DuckDB, it uses a smart storage. So it's column first instead of row first. And through that, it can do a lot of smart pre-processing to filter down data, so it actually limits the amount of data being scanned. It uses really fast joins and modern processing. And today we're going to be really diving deep into how graph databases typically worked and how Kuzu improves on top of that. And when you want to go really deep into knowledge graphs, I think you can take away a lot from this episode. Let's do it.
Kuzu is an embedded graph database. So basically what that means in modern jargon is that we implement Cypher and we are a library. We can put us into your scripts, you can put us into your Android applications, you can put it into AWS Lambda, and you can put it on many environments as a library instead of setting up a server somewhere and then connecting to the server. So some of the use cases that we see are related to the fact that we are embedded. Some of the use cases that we see are because we have an in-memory mode or a ephemeral graph mode, meaning that we don't persist your databases. You just build it on the fly and then throw it away. And then some of the use cases we see are people building very large databases, and they have frustrations with other existing graph databases, and they come to Kuzu because Kuzu is a state-of-the-art engine in this space. So we essentially see, if I were to categorize the use cases based on the sort of the features that we have or the properties of Kuzu, I'd say they would bundle in the embeddedness, the fact that we allow people to build ephemeral graphs, and the fact that we scale very well on large databases. Originally, Kuzu started as a research project because we were going after scalability and performance. And some of the usability decisions that we did, such as being embeddable and having an in-memory mode, has also been advantageous in terms of getting some use cases. So let me give you an example from, for example, this one use case that uses us as an embedded system and also uses this in-memory mode. This is something we wrote about. This is a user called Bauplan. And what Bauplan does is that they basically give you so it's a function as a service company. What that means is that they allow you to build complex applications, serverless applications that consist of many serverless functions working together. And what they're trying to do is give you a good development interface where you write your programs. Maybe this is a data processing pipeline that you're writing that consists of, say, 20 different AWS serverless Lambda functions that work together. And you write it in Python, as if you're writing essentially different functions in Python, putting it together, and then they will compile it to these serverless functions and run it for you. And as they do this, they will actually optimize and also do some debugging whether your program is correct or not. So what happens is that when somebody clicks on, say, writes a program in Bauplan's interfaces, Python interface with maybe like 20 Python functions, each that will compile to serverless functions, and they click on compile and run. What Bauplan does is on the fly generates this graph of the computation that will happen. and it will do some optimizations to minimize the data that will be transferred between these functions, which is going to save the user a cost, AWS communication cost, and serverless function running time cost. And also it will do many sort of checks about the correctness of the program. And they do this essentially within a second or a half a second. They run hundreds of queries in Kuzu, create a small graph and hundreds of queries in Kuzu. So they needed, this is a case where having an embedded graph database where you are creating on-the-fly graphs and throwing them away is useful. So this was something obviously surprising, because that's not how we started Kuzu at all. Kuzu went for the billion scale graphs, but this was a case where essentially we benefited from some usability decisions that we made that are really orthogonal to the scalability and performance decisions that we made.
Yeah, and I think that already leads us a little bit into the more technical aspects. And you already mentioned that Kuzu is also one set of the use cases is because people are unhappy with the existing graph databases. I want to move a little bit into what are the different features that actually makes the performance of Kuzu better than its competitors.
Yeah, so I can tell you a little bit about kind of the origins of Kuzu and how Kuzu started. So Kuzu it's a spin-off from a research project that I had that started about 4 years ago. But prior to that, about 5-6 years ago, before that, so maybe at this point, maybe 8-9 years ago, I have entered this space as a researcher, this graph database space. And when I entered this space, the first thing I did was I did a user survey. So this is published in VLDB and VLDB Journal. And the question we asked people were basically, what do you do with your graphs? How large are your graphs? We wanted to understand their graphs and their use cases. What type of applications do you build on graphs? And we wanted to understand what are your main challenges with existing technology, basically. And this is prior to me starting with my research group any kind of technical project in this space. And what we learned in that user survey, and this was a user survey of about 90 people online, and then we talked to maybe 15 people face to face. What we learned is that a lot of people had major scalability problems. So there was this association that you can't essentially manage large-scale graph databases. Graphs are hard because graph queries are hard, and existing technology doesn't scale. And it was very visible. Like scalability was the top sort of problem people consistently told us in that survey. And I think it was actually the highlight of the paper was that scalability is an issue. So my tenure case, actually, when I took my position at University of Waterloo, was to study that problem, that if we were to develop a modern graph database engine, what would its architectural principles be that would make it scale and make it perform? About 5-6 years of research and lots of articles that we run, several theses in the topic I advised. After all that work, I had a clear sort of picture of what that system would look like. So some of its core principles. So one of the principles was that I was convinced that the system should be columnar. That sort of the storage essentially layer of the system, the physical design of how we're going to store the records should be columnar instead of row oriented. So in a system like Neo4j, for example, the physical storage of records it's closer to row oriented. It's even linked list based. It's an interesting kind of very update friendly, but not very scan friendly design, where you have essentially, let's say, a node record, and node records will point to their first edges, and then the first edge is going to point to its second edge, so on and so forth. But there's no kind of concern for locality of all these records on disk. Whereas in a columnar design is optimized for scan performance, where you want to put data that will be scanned essentially that will be scanned together, and it allows also for you to compress the data. So it really optimizes for scan performance and minimizing disk IOs when you're doing large scans. So the insight for why I thought a graph database should be columnar was that a lot of the queries that people ask, first of all, they scan large chunks of the database, because graphs essentially people do a lot of traversal based queries. Okay. But they usually are going to read as they do these traversals, as they find the patterns or the paths that they're looking for, they're going to read a few of the properties of these edges and nodes. So a columnar design is good for that because it first separates different properties from each other. So if nodes have, say, 20 properties, but a query only accesses one of them, you get an ability to essentially touch a very small part of the node records. So that was, for example, one so storage level architectural decisions. We had a paper on this back in, I think, 2019 or 2020 in VLDB. It was a thesis that I advised. Another thing was that I worked a lot on several core query processing techniques, novel processing techniques, I should say, that are specifically designed to address the scalability challenges that happens during query processing on graph patterns. So a fundamental kind of property of graph queries is that graphs generally represent data where there's a lot of many-to-many connections. So classic examples are just social networks or financial transaction networks, where an account, for example, might transfer a lot of money to a lot of other accounts. So that's a many-to-many relationship. And those accounts may be transferring money to many other accounts. So if you're looking for a path, there's this, by the nature of the query and the nature of the data, the search space within which you're looking for a pattern grows exponentially. So this exponential growth is essentially a major problem with scale, like essentially querying over large graphs. So just a simple math. If on average each node has 1,000 connections, if you do a 3-hop query, you're essentially looking for a search space of 1,000 cubed, 1,000 times 1,001. So it just grows. So that's just already a billion possible sort of patterns within which you're looking for some pattern that you're searching for. So I advise a lot of sort of work on, we did a lot of work on addressing this problem. How could you essentially mitigate this growth? Can you do some optimizations when during query processing, instead of essentially enumerating a size of, say, 1 billion in my example, you can do something much smaller and look for a pattern in a smaller space. So there, one sort of very good technique in the space is factorization. Factorization is essentially a compression technique, but it's very interesting because compression in databases is almost always used at the storage level. When you're storing your records, you compress them so that you minimize I/O. But factorization is a compression technique that's designed to compress the data, the intermediate data that query processors generate, not the ones that you store on disk. So it will, for example, factorization can take that 2-hop, 3-hop queries and then represent it in a much more succinct way. So I can get into the details of that, but we did a lot of work about how do we essentially increase the scalability of these systems, query processing scalability, if you will, so that some of these harder queries can be answered in a much more performant manner. So all those essentially techniques that I had, and some of these I can see we can get deeper into. So all of these techniques were results of many years of research that we did, and at the end of which we said, okay, let's put all of these together in a new system, and Kuzu is that system. That tries to integrate all the state-of-the-art knowledge we know about how to manage and query large-scale graphs.
And to maybe nail it really home to the difference between especially like row and column based, can you maybe go into one example of how a query would look like if you do it row based versus doing it column based, and like to really nail the point home of this like escalating complexity that I don't have so many different options to query through?
Yeah, so I can give a very simple example. So for example, and this is not going to be graph specific, but just so that I can clarify the difference between a row-oriented storage and a column-oriented storage. So if you take, let's just focus on relational systems. If you take a system like Postgres is row-oriented, has a row-oriented storage design. What that means is that if you've got a table of, say, let's say accounts, okay, and there's maybe 20 properties, the owner, the address of the owner, the balance, the date it was opened, so on and so forth, right? The way this will be stored on disk is that there will be one record, okay, that stores 20 properties of that, each row essentially next to each other. And once that is finished, you'll have the second record and then the third record. In a column-oriented system, what you'll have is that you'll take the first property, say maybe the name of the owner, and the name of the first record and the second record and third record, all of those will be stored next to each other. And then in a separate part of the disk, you'll store, say, maybe the balances of each of these accounts, one after another. So the balance of the first account will be the first integer, the balance of the second account, so on and so forth. So you essentially split each record into 20 pieces and then store essentially in 20 different contiguous sectors each property or each column of this record. And if you get a query that, for example, looks for something selective, give me all accounts that were opened on a particular day. Now, what you can do is you can essentially scan only the property. You don't need to scan each record and then essentially on disk, essentially, you don't need to scan all of the database. And maybe the whole database is 100 gigabytes. But let's say only the date properties when the accounts were opened is maybe 500 megabytes only. If you just put all of them together. So you can only scan the 500 megabytes and then find the ones that were opened on a particular day. And maybe there's 2 records. And then you can go do 20 different IOs to consolidate the rest of the properties. So that's a case where you can, instead of scanning 100 gigabytes of data to find those records, scan only 500 megabytes of data. And that will give that's essentially one of the main insights of columnar databases in general. And that's a topic at this point 3 decades old, and it's span of many systems. Modern analytics-oriented systems do column-oriented designs. And our insight was that a lot of the graph queries are analytics-oriented. So instead of optimizing the system for updates, we optimize the system for scans. So that's essentially the justification for why a system like Kuzu is columnar.
Yeah, and how this maybe as an example would look like if you have a social media graph. I think that this is the dominant example. You basically have a query. So basically I have a user, let's take me, Nikolai Gerald, and I want to find like people who are followers of my followers. Yeah. So instead of basically, I first have to identify like the starting node, which is me basically. So I find it. And then I basically filter down with the columnar database, like node which have a follow connection to Nikolai Gerald. And through that, I don't have to do the row retrieval. So basically, I get the row where Nikolai Gerald is in it. And then I basically have to get all of the different edges, follow them, and then basically do another hop to follow them again. But I can use the different separate columns to basically filter them down already and decrease my search space.
So this is, I think, partly accurate, but let me maybe separate 2 things. So a columnar sort of record storage is orthogonal to, I think, another thing you're mentioning in your example, which is the ability to follow essentially specifically your connections. So that's a feature that graph databases have that relational databases does not have, which is that when you in a graph database say, here are my users and here are other users that they follow. Here are the follow essentially relationships. What graph databases universally, not just Kuzu, Neo4j, but take any other graph database. What they'll all do is that they'll build a join index automatically. You don't have to, as a user, tell the system to build this index. The system will automatically build a join index. So what that means is that they will build an index so that for a particular user, say Nikolai, you'll be able to find the people Nikolai follows and the people that follow Nikolai with a single IO. So that's essentially an index structure that is separately built automatically in graph databases. And that's, in some sense, that's orthogonal to the columnar design that I was talking about. So in my example, I gave a columnar essentially design of node records, but you can also have a columnar design of these relationship records that are being indexed. So for example, if your follow relationships had many properties, on each follow relationship, maybe you put many properties, like maybe the date the following started, or how many times they have seen each other's posts or something. Now, all of those properties also need to be, so those are relationship records. They also need to be stored somewhere. And Suppose you can again make a choice there as an architect of the database. Do I want to store these properties of these relationships in a row-oriented manner or in a column-oriented manner? And in your query, for example, your query doesn't care about the date the following started or how many times essentially these people have interacted. So in a column-oriented design, you can essentially avoid scanning any of those and just scan essentially the fact that they're connected to each other, which is usually another kind of property of the relationship, and completely avoid scanning any of the properties of these relationships. Whereas in a system like row-oriented system that forces you to scan the entire records, relationship records, you are forced to scan also all the properties that come with the relationship record, this follows record, that you may not be needing for the query processing. So columnar versus row-oriented is essentially a choice about how much of the records do you want to read when you're answering the query. And columnar systems gives you the advantage that you can read as few as parts of the records as the query needs. But obviously there's a catch. The catch is that when you're producing your final outputs, you have to do extra work to go and grab the rest of the records. That suppose you want to find the users that Nikolai follows, right? And maybe when they follow, and the day the following started. So like you are trying to return some of these properties. So columnar systems, maybe to find the final set of records, does scan little, but at the end they need to go through an extra step to make sure that if the final query output requires other properties of the records that were not maybe needed for the query processing or to find the records, but that are needed because the user is returning them, right? Now you need to do extra work to put things together. Whereas in a row-oriented system, because you've scanned all of the entire record during query processing anyways, you can just directly output them. But overall, it's very well understood that if you've got a system, you're building a system that is meant to be analytics-oriented, that's meant to optimize for analytics-oriented applications, meaning applications that ask a lot of queries, but maybe they do batch updates instead of a ton of small updates. They're not OLTP type of applications. Columnar systems they've got a big advantage.
And in this traversal, how do CSR, so compressed sparse rows, come into play for the traversal or for the adjacencies?
Yeah, so CSR is a specific physical design for the join index that I mentioned. So there are different ways you can store the join index. The join index is basically allows you to locate all the relationships of a particular node very, very quickly. You should think of it as with a single IO, with a single lookup. You can find any of your nodes relationships, or at least start scanning them. So there's, again, in the storage of that index, there's different designs. You could obviously build a tree-based classic index, B plus trees, and try to have a join index. That will also give you quick access to sets of records. CSR is a particular physical design that's very popular for graphs. In general, in memory, graph analytics libraries use CSR-based indices a lot. Kuzu builds a disk-based CSR index. And CSR is basically, you can think of CSR as, it stands for columnar sparse row. So actually, we can edit this maybe. CSR should be standing for, let's look it up, columnar. Let me find this. Sparse row, I think, but I want to make sure. Compressed sparse row, sorry, not columnar, yeah. Compressed sparse row. But it's essentially a columnar. The reason I always get confused with this is, we can edit this part. So CSR stands for compressed sparse row based storage. And what a good way to understand what that is, so if you have essentially, say, from to, okay, so that's the relationship, the essence of the relationship that you're storing, okay? You got from nodes and you got to nodes. And let's assume that these from and to are integer IDs that identify the nodes. So 1 to 2 means node 1 follows node 2. 2 to 5 means node 2 follows node 5. And you got these records, 1, 2, 2, 5, etc. So that's your essentially essence of the relationship. Again, the relationships could have other properties, but let's ignore that. The join index does not usually store those properties. So if you got a from column and a to column, and they are IDs of these nodes, and if you sorted, say, the from column, sorted these records by the from column, you're going to get something like 0, 1, 0, 5, 0, 7, 1, 2, 1, 5, 100, 2, so on and so forth. So the from column will be sorted. And now, if you compress, now that the from column is sorted, you can do run length encoding compression to it. So run length encoding compression basically says if essentially there is 0, the from column values are like 0, 1, 0, 5, 0, 7. That means there's 3 zeros. So you just store 0 and 3 instead of storing 0 3 times. And maybe if there's 5 ones next, then you store 1 and 5. So if you did that sort of storage, that is actually the essence of CSR storage. CSR storage is very similar to essentially storing all the 2's consecutively. And then from the from column, you store just essentially how many edges each node has, and you don't necessarily have to store anything else. So you essentially end up compressing the from column a lot. And if you're storing the backward edges, now you would have a to and from relationship, and then you would sort by 2 and compress the 2. So that's the essence of compressed sparse row. It's essentially, that's why it's a columnar storage as well. And Kuzu stores on disk its join index in this compressed format, in this CSR format. And that contrasts with, say, Neo4j. Neo4j stores these records, it links these records with each other, and doesn't have the guarantee, for example, that the records of a particular, the relationships of a particular node, the follows of, say, Nikolai, are not necessarily next to each other, but they're linked to each other. So you can, with one IO, always go to the next index. But obviously, there's no locality guarantee as the database grows. Kuzu instead always guarantees that we'll always store the edges, the relationships, that index in this CSR format.
Interesting. So we've talked a lot about the storage or memory layout of Kuzu. What we've missed until now is the compute part, and especially the vectorization and how it makes the queries more efficient. Can you go a little bit into the vectorization part and explain it, how it works and how it contrasts to regular graph databases?
Yeah, so this is also, again, a vectorization is not a very graph database specific technique. It's a technique that originated in columnar relational systems in essentially late 90s or in 1990s and 2000s. It's very widely used now for, again, analytics oriented systems. In columnar systems, this is a widely used technique. And what it contrasts with is more traditional database query processing architecture, which is called tuple at a time processing. In basically all database management systems, relational systems, graph databases, or even RDF systems, any system that implements a high-level query language, ultimately what happens in those systems is that those high-level query language clauses are compiled down into a expression tree, a relational algebra expression tree, whose roots are scans of tuples, and intermediate nodes are some relational operations like maybe joins, maybe projections, maybe aggregations, so on and so forth. Imagine essentially a very simple expression tree. Let's look at a very simple query. So maybe count me all the nodes that have name Nikolai, whose name are Nikolai. So a very simple expression tree for this, that there's going to be a scan node that scans your nodes, so maybe say user nodes, and then a filter. This scan could also be implementing the filter, but let me just simplify it. But let's assume there's another operator called filter. What it does is that it just checks if the tuples that it receives have name Nikolai. So it's going to run that expression. And if it does, it's going to give it to the next operator, which is count. So there's three operators: a count operator, an aggregation operator, a filter operator, and a scan operator. In a traditional tuple at a time processing, what happens is that the processing starts from the count, and count says to its child, which is filter, give me your next tuple. And then the filter calls its next child, which is scan, says, give me your next tuple. And then they pass essentially one tuple between each other until you exhaust the scan. In vectorized processing, what happens is that the disadvantage of this very old architecture now, and not a lot of systems I think are built this way. Certainly not a lot of analytics oriented systems are built this way. But it's got the advantage that it's very simple. But it's got the disadvantage that there's a lot of essentially function calls that happens between these operators. They keep calling get next tuple. For if you got a billion tuples you're scanning, you're going to call essentially maybe, like in my example, 3 billion essentially get next tuple calls. Vectorization, this technique called vectorization, I think a better name for it is block-based processing. That appears in some literature. It appears as block-based processing. What block-based processing does is that it passes instead a block of tuples between operators. Each time you say get next tuples, you essentially get a block of tuples, like 1024, let's say, or 2048 tuples. So it amortizes this expression, the cost of calling these get next tuples function calls. So what happens is that now you need to rewrite your operators, though, because your operators can no longer assume that they're getting a single tuple. They all need to be rewritten. Every single primitive operator in the system needs to be rewritten in tight for loops, which is actually very good for instruction locality as well. So it's well understood now that this type of vectorized processing is good if you want to essentially build a query processor that is designed to process lots of data. Because so analytics oriented systems make this assumption that their query processor are going to essentially compute on a lot of data passing through these operators. Vectorization is essentially a common wisdom architectural principle that minimizes these calls, which compares also, again, systems like Neo4j to the last that I looked at it was this is this tuple at a time processor. So those are essentially all architectural principles have this performance disadvantages if you're building an analytics oriented system.
Yeah, and for me, yeah. Go ahead.
And but I want to be clear, that's not really a graph database specific optimization. It's essentially an optimization that any system that is being built to be optimal or optimized for read optimized query processor. If you want to build a highly optimized query processor that is designed to do a lot of computation on a lot of data, then vectorization is a good idea. It doesn't have to be graphs, relational or RDF. It's just a good idea to optimize your processor to work on a lot of data.
Yeah, and it's in the end taking advantage of modern hardware.
That's right.
Especially we see it in a lot of different databases because we have more powerful computers. We don't need so many distributed systems anymore. So we can go back onto single node and take advantage of something like vectorization.
Yeah, exactly. Yeah, I completely agree. A lot of these common wisdom techniques, if you put them together, essentially pushes the state of the art. Certainly in graph databases, I think a lot of the graph databases that we studied were not built with these common wisdom architectural principles. And some of these are, again, not even graph database specific. They're just general broad data management principles. And they were built on these older architectural principles. So that's one of the gaps that we saw, was that there's a need for a state-of-the-art system that sort of puts some of these common wisdom architectural principles along with some of the graph-specific ones that my research group did together. And Kuzu aims to be such a state-of-the-art system.
Yeah, and I think that's a cool part in data and AI. You basically put together a lot of optimizations to arrive at the state of the art and don't have one single core idea, but you pick and choose from different areas, from like systems engineering, networking, more like the hardcore like data engineering side, put it together to build like a system that's better than what we have seen so far.
I agree. I think it's in the nature of a lot of system oriented projects and products that the whole is much bigger than the parts. There's a lot of parts that you have to do, but a lot of them don't require a lot of innovation. You just need to follow, I think, the modern state-of-the-art principles. And this happens a lot in databases. Every decade or so, the field moves and we understand better how to build sort of modern, fast engines. And then the newer systems are able to adopt them. And the older systems are just much harder to adopt those principles. And it's, I think, in the nature of the field.
Yeah, and we touched on a lot of the technical aspects of Kuzu. One thing I want to go into as well is the ASP join, and not like the complete technical details, but rather the core ideas behind it and what it replaces and how it improves on the existing join algorithms we have in graph databases.
Yeah, good. So I think to explain, so ASP is the term we used in the Kuzu paper, in the Cider Kuzu paper. And that was published before we even became a company and spun off to commercialize. In the actual implementation, we use, I don't know the term that we use for that join operator, but we essentially, let's call it ASP. I think we call it multi-way join or something, but I can get into the principles of what we were trying to do. But to explain that, I need to explain factorization a bit better. So I gave a high-level overview of what factorization is, that it compress intermediate relations, intermediate sort of tuples that are produced during graph sort of pattern querying. So the example that I gave was like a few hop query about maybe the accounts that Nikolai's account transferred to, and maybe two hop accounts. So let's maybe take another simpler example. Suppose the query is, give me all the two path transfers that Nikolai could be facilitating, meaning that Nikolai's account, you got an account, one account node. Let's call it account N, account Nikolai. And that node has some incoming transfers and it makes some outgoing transfers. And somebody is, let's say, a fraud analyst is interested in to see what sort of money flows could Nikolai be facilitating, that it's the middle person in these accounts. Okay. So if you got essentially 1,000 incoming transfers and 1,000 outgoing transfers, so there's essentially the two paths that Nikolai's account is part of is 1,000 times 1,000. There's 1,000,000 possible different combinations of two path money flows that Nikolai could be facilitating. Okay, so which means that there's actually, if I ask you that query in Cypher, match maybe a node A that has transferred money to node B that has transferred money to node C, where the middle node B is owned by Nikolai. The output of that query will contain 1,000,000 tuples. Okay, just even though there's only sort of 1,000 incoming transfers and 1,000 outgoing transfers, the sort of the fact that this many-to-many joins or the many-to-many sort of pattern growth leads to a very large number of patterns. In factorization, a different way you could have stored that. So take any relational system and run an equivalent SQL query. That system is going to, in its query processor, generate really 1,000,000 intermediate tuples and materialize it in memory. It's going to flow through memory, but it's going to materialize it. But an equivalent way you could have represented that 1,000,000 tuples is, you could have represented as Cartesian product of much smaller pieces. You could have said, my intermediate, that intermediate relation is 1,000 incoming sort of incoming transfers, Cartesian product that with Nikolai's account, and Cartesian product that those two with 1,000 outgoing transfers. Now you got essentially a much more compressed representation that contains only roughly sort of 2,000 records. It does represent 1,000,000 records, but in memory, you only represented it as 2,000 records. And suppose all you want to do is count the number of you could be facilitating, number of two-path flows you could be facilitating. Now, I don't even have to ever uncompress it. I can just very quickly count the number of tuples there. It's 1,000 times 1,000. I can say the correct answer is 1,000,000. So factorization is this idea. It's that idea that when there are many-to-many joins, you can represent the intermediate results relations that are generated in a much more compressed way by using Cartesian products of sets of records. So that is the idea of factorization. This ASP join that we were trying to do, It's very detailed. It's going to be difficult to explain each component. But it was essentially trying to get good factorization structures, which means good Cartesian product structures. And it was also trying to make sure that one thing we wanted to avoid in Kuzu was, and a lot of graph database systems do this, is that we wanted to avoid sequential scans as much as possible. So what do I mean by this? So if you got essentially this 2-hop query, Nikolai's, so let's maybe take another query. Nikolai's sort of 2-path transfer where Nikolai is the originator. A common query plan for this query, now I'm making the A node Nikolai's account, is you go to Nikolai's accounts, and maybe there's 1,000 of those, and then for each one of those, you go to 1,000 other accounts. And if you need to scan some properties of these accounts, a common sort of, it's a very bad query plan, is that you essentially get non-sequentiality when you go to Nikolai's accounts. You're going to 1,000 different records, but there is no guarantee that they will be located consecutively on disk. And when you go to their accounts, you lose even more locality. So a very bad way to process this is that you go to Nikolai's account, and then from that do another random IO to go to 1,000 other accounts. And then you go to Nikolai's second account, do another 1,000 random IOs, and so on and so forth. That's a very bad way to process this. And our observation was that relational systems never do processing like this. What they do is they use hash joins, which means they'll take essentially maybe the accounts and the transfer tables, and then they'll always scan sequentially, and then any randomness will happen in that intermediate hash table lookups. So what we wanted to do was to also ensure that we behave like a relational system's hash joins in the sense that we always scan sequentially when we do these sort of graph pattern evaluations. So ASP joins components, and I won't be able to explain the full ASP join because that's a little, it's going to get, I'd need to get very low level, and I need maybe a board to explain it. But it was essentially the problem we were trying to solve is that we wanted to get good factorization structures, plus we wanted to ensure that we always scan sequentially. And what our realization was that a lot of the times these conflict. A lot of the times you can't get good factorization structures and get sequential scans. So what we had to do was apply this technique called sideways information passing, where sometimes we store some intermediate data in memory, figure out what needs to be scanned, pass that down to the scans as information, and the scans are going to make use of this information about what are the successful joins. So which records do I need to scan? So it's very hard to, as I'm explaining this, I'm realizing it's very hard to explain something like ASP join. But there's essentially this core idea of trying to get good factorization structures, trying to ensure that scans are sequential. And sorry, the third piece that we were trying to get is that graph databases has the advantage that they have the disadvantage of doing these non-sequential scans, but they always scan only the parts that they need. So they don't, so for example, in that example that I gave of 2-hop joins, even though you're doing non-sequential scans, you're never scanning any record that you never need to. So you're doing them randomly, maybe. You're going to your degree first neighbors, but you're always scanning something useful. And that's something relational databases don't have. Relational databases, when they join things, they'll scan the entire tuples. Even though you need maybe only Nikolai's 1,000 records, transfer records, if your transfer table contains 1 billion records, they'll still scan all 1 billion records. So that was the third thing we were trying to get, and I should have clarified that. And if you want to get that as well and make scans sequential, what you have to do is that you build these hash join type of plans where you get essentially some, maybe your Nikolai's record, and you understand that you need to only scan Nikolai's transfers, and you're going to pass that Nikolai tuples information sideways to the transfer table scan operator and tell the transfer table's scan operator, only scan, give me nodes that have this Nikolai's accounts ID, maybe account 7. Only scan me the sort of transfers where the from account is 7. So you can avoid scanning all 1,000 records or all 1 billion records. So you can only scan that 1,000 records. So we were essentially, so maybe to summarize it, we were essentially trying to behave like relational systems hash joins, but have the ability to A, do factorization, and B, only scan the parts of these relationship records and node records that really needed to be scanned, which was an advantage of graph databases. But the traditional processing in graph databases was something we didn't like much because of the non-sequential scans that it leads to. ASP join was our solution, and it is one of the core join algorithms that is implemented in Kuzu.
Yeah, and I think it's one of the downsides of columnar databases is writes, and especially also updates.
That's right.
So usually in something like Parquet, which is also columnar, you delete the file and you basically create a new one.
Yeah.
And how long in Kuzu does actually the write path take until it's also indexed? And also a little bit on that is, should you optimize for actually having more of a read heavy workload with Kuzu and, for example, like batching writes and minimizing concurrent writes with it?
It's a good observation. I think it's like a fundamental sort of design decision that you make when you're starting to build your system. Do I want a system that's optimized to take in small writes very fast, build an OLTP like engine? Or do I want a system that is optimized for analytic queries, which means read heavy queries? And we consciously made the latter. We are a read oriented system. So you are right that columnar systems, because of certain optimizations that they do, simply just the fact, for example, that you separate each record into, in my example, there were 20 properties into 20 different kind of column, like different parts of the disk, means that if I insert a single tuple, I need to write to 20 places, right? If I had a row-oriented system, I could write that record consecutively to a single place, which means you only have to do one IO, for example. There is this fundamental sort of trade-off that you make. So you can't get both of these, I think. You have to make a constant. But it is fair to say that columnar systems, and Kuzu is one of them, we are more performant if you batch your writes and do your writes in batches instead of doing a lot of sort of maybe, 10,000 sort of simple transactions, each one kind of adding one relationship or one node record. It's not a particularly a case where you're going to perform very strongly. But there is certain optimizations that we do to to reduce essentially the time that it takes to commit transactions, write transactions. This is particularly a problem with the join index. When you do CSR-based join index, right? The original design of CSR is that everything is packed. There is no, so if I want to, so suppose Nikolai's account is node 7 and node 7 has now a new transfer. That will go into the join index. But the way I described the CSR index was there's no gaps for me to add a new edge in that the second column, right? So, for example, what we do in Kuzu is that we actually, that second column that stores the actual neighbor node IDs, if you will, actually contains gaps between each sets of, so after node 0 sets of edges, we store some gaps. After node 1's sets of neighbors, we store some gaps so that we essentially amortize, we make it more update friendly so that if you get a single insertion, Nikolai gets another transfer, we can essentially, there's usually going to be a gap there, so we can directly write it at the end instead of resorting and reshuffling the entire column. So we do several optimizations like this. So if you're familiar, there's a popular data structure called packed memory array. So packed memory array is essentially a way to sort elements by leaving gaps. And that kind of compares to tree-based indices that also sort elements or sort records. So our columnar design for the join index, this CSR based index, is essentially based on packed memory array. So we amortize, we make that columnar storage more update friendly, for example.
Yeah. To maybe close it out, I think graph databases are gaining traction at the moment, but it's still very hard to adopt. What would you say is missing to make it actually easier for developers, especially, to adopt graph databases? So what's like a missing link?
It's a hard question to answer. So part of the reason graph databases are going to remain a niche sort of industry is because relational systems, the amount of education that exists on relational systems is incomparably larger, or there's a lot more education on relational systems than other classes of database management systems. So every computer science curriculum in the world teaches a database course, and in that database course you're going to learn SQL. So there's a lot more familiarity with SQL, and I don't think you can compete with that. I think graph, so there are essentially directions, I think, that could increase the popularity of graphs. There's a couple of waves too that could increase the popularity of graphs. One of them is if you try to build systems that can essentially, and property graph databases, the one that Kuzu is based on, which essentially follows Neo4j and the class of systems based on Neo4j. Property graph database systems has the advantage that the data model, even though it's graph oriented, even though it's object oriented, it's actually very close to the relational model. So basically you have node records, basically have tables of records, but each table you just indicate if it's an entity or a relationship. So that's like the primary difference between the property graph model and the relational model, especially Kuzu's version of property graph model, where we force you to predefine your schema, is that you have tables of records, but you just need to tell us, okay, this account table, that's actually an object, that's actually a node. Whereas this transfer records, that's actually a relationship. So that's the difference. You give this additional information, and based on that information, we optimize this. But to come back to my point, graph databases, the property graph database, has the advantage that because they're so close to the relational model, it's actually very easy to understand. And if we build essentially features on these systems that make it actually easier to query directly off of relational records. So suppose you got, say, CSV files and you got Parquet files. A lot of people dump their records in these tabular formats. These formats are essentially sets of records, right? So sets of records identify certain information in your data model. So they could be identifying your accounts and the information of your accounts. If we built features around these systems that even close the gap between where, okay, these sets of records I want to model that are in CSV files or Parquet files, I want to model them as nodes. And then these other sets of records, they're my edges. So you're now even closer to the relational model because you're just providing some kind of mapping. You're not even doing a big mental step of representing those Parquet files in your graph database system. It's more like you're doing a mapping saying, okay, you're saying like the graph database systems are able to query tabular formats as well. So I think that could essentially, if you had features that allowed you to do this, say like a system like DuckDB can scan and query over raw Parquet and raw CSV files. And you can build similar features in graph databases as well. That's something we are doing prototyping on in Kuzu. How do we build features that allow you to query these raw tabular records also in the form of a graph? I think that could also simplify. The more you simplify essentially querying records as graph, the more you can contribute to popularizing graph databases, I think.
Yeah, and what's next? So what's on the horizon for Kuzu? What are you building on? What can you already teaser?
Yeah, great. So we've got several sort of major features coming up in the first quarter of 2025. of them is that's going to come very soon is we're going to have a WASM version of Kuzu. So you'll be able to run Kuzu in the browser. We already have a version of this. We are essentially testing it. It's very close to being released. So there were a few people who asked for this, something that you can run in your browser, a database that runs in your browser, a graph database that runs in your browser. So that's coming up soon. That was one of the environments where you couldn't run Kuzu, but hopefully we'll close that gap. And then we had not built a lot of indices around the system, and we're building two indices right now. One is a vector index, so you'll be able to do nearest neighbors queries over the floating points that you store in Kuzu. You can already do that, but we don't have a fast way of querying or finding nearest neighbors. And a lot of RAG and LLM based applications that want to experiment with techniques, retrieval techniques, require that feature. So we're building that index, and we're building a full text search index. So there's several core retrieval functionalities that Kuzu is getting. And finally, the next thing that's immediately coming up is we were lacking a graph data science library, like a package of off-the-shelf graph algorithms you could run. Say you got a graph and you want to say, I want to run PageRank, or I want to run connected components, or I want to run between centrality to run these batch graph algorithms. You'd have to so far move. We had integrations with some graph libraries like NetworkX. You could take your graph and in Python, and not in maybe other APIs we have, but in Python, you could, with a single function call, convert the query results into, say, a NetworkX object, and then in NetworkX run those graph algorithms. But that has scalability problems as well as performance problems. What we are providing is now off-the-shelf procedures that you can run directly in Kuzu's Cypher dialect and run those algorithms and compute those graph algorithms. So those are the four things that are immediately coming up.
Nice. And if people want to start building with Kuzu or want to learn more about it, where would you point them?
I think come to our documentation website, and there's a getting started part. We have a browser-based command line interface with a graph visualization. That's a nice tool to use to get started with Kuzu. It's called Kuzu Explorer. So I'd advise getting started in our documentation page and using Kuzu Explorer.
Nice. And if people want to follow you, where can they do that as well?
We have a LinkedIn and Twitter Kuzu page. I think that's the best place to follow Kuzu related things. I'm not particularly super active on social media. And we have an AI engineer, Prashant Rao. Prashant is a lot more active than I am. So Prashant usually breaks all the news related to Kuzu. And please sign up for our newsletter. There's a newsletter on our website. If you come to kuzudb.com, you can sign up for our newsletter as well and follow the developments around Kuzu.
So what can we take away when we are building our applications? So first of all, I think we went way deeper into one specific technology than I usually do and really focus on one library. But I think it can teach you a lot when you're developing libraries or new tools as well. I think in a lot of the stuff we are using nowadays is a little bit older and doesn't apply a lot of the techniques and optimization we can take advantage from through the modern hardware. And we see, especially with Kuzu, but also with DuckDB and Polars, that we can do so much on a single node or embedded on users' devices because the hardware is so powerful. We just need to optimize the stuff to actually take advantage of that. And here, like Kuzu does a lot, like vectorization and stuff like that, where you suddenly can run stuff where you actually needed a really complex database before, but now you can do it in memory. And through that, you can apply to a lot of stuff. So for example, like if you're using knowledge graphs with your LLMs, you can use Kuzu as a backbone. We had in the interview a few weeks ago with Robert Kork from Ask News, they are basically building knowledge graphs for the user-specific query on the fly and then query it. And I think this is something you can do here as well. So in your application, you likely are always querying on subgraphs. So you basically construct a subgraph, load it into Kuzu, query it, and then you go on. And for that, it's way more efficient than having a standalone graph database, because you don't deal with distributed databases from the get-go, where you actually have to do really complex joins on UUIDs and stuff like that. What I think is really interesting is the graph data science part or graph algorithms at large. They are interesting for some applications, but they are, in my opinion, rarely used. So it's often like recommendation systems, really large scale recommendation systems, fraud detection, or influence analysis on social networks. But for like most of us, probably the advanced query algorithms aren't worth it, or they are so deep into optimization that we will likely never get there, because we can get a bigger bang for our buck with simpler techniques. For RAG, Kuzu's is suitable in my opinion. I think in general for RAG, before you start with something graph-based, first make sure that you actually optimize the rest of your retrieval as well. Because I think like you have bigger bang for your buck in vector and keyword search than with putting a graph on top and then also like adding smart metadata to the different documents. So before you add the graph, then basically optimize these two components and then add the graph, but have a clear reason to do so, why you actually can't do the same with simple metadata tags. And yeah, I think Kuzu gives us a lot of different directions of how we probably will build in the future. So first, it's embedded by design. It's a library and not a server. So it's a graph database that runs locally, so you can integrate it into scripts, mobile apps, serverless environments. I think we will see more and more of that, because our devices become more and more powerful. So on the server, I can run more on a single node, and also I can push more onto end user devices. A second one is use columnar storage, and this allows you to actually have a way better scan performance. And also it improves the I/O efficiency and also compressibility. So basically you can compress the data better. And then you have like the vectorized query processing, which is also like with today's CPUs, you can really take advantage of the CPU cache more by doing vectorized queries. And lastly, I think like what they have done with ASP join and vectorization, it pays to have people who really can optimize the shit out of an algorithm. Whether it's actually necessary for your own use cases, that's something you have to know. I think like for libraries, it's always something interesting to build in, but only if it actually makes sense for you as well. But yeah, that's it. Let me know what you think. We went really deep into Kuzu. I think the architecture decisions behind Kuzu were really interesting, and also the different use cases you mentioned, like what they are working on, what they are thinking about, and how Kuzu should be used. Let me know in the comments what you think. Otherwise, I will catch you next week. See you.